Bismillahirrahmanirrahim. Let's talk about our lecture 1, session 2 of our course Advanced Engineering System Optimization and Simulation. So, let's talk about system. What is a system? So, according to Eisner, systems normally are composed of hardware, software, and human elements, all of which must interoperate efficiently for the overall to be effective. Eisner was basically a professor in the George Washington University and did many projects for the Department of Defense. And his projects were mostly related with systems engineering. Second definition could be a collection of hardware, software, people, facilities, and procedures organized to accomplish some common objectives. Another definition could be a system is an assemblage or combination of various elements or various parts forming a complex unitary whole. Um, Again, a system is defined as a group of components that work together for a specified purpose, and that's probably a very or simplest definition of a system. Last one is all definers will agree that a system is a set of parts coordinated to accomplish a set of goals. So here we have various authors and they are providing us various definitions of system. So in a nutshell or in very easy words, in very simple words, we can say that okay, in a system, our a system has got sub parts or sub elements, and then uh, different parts are working together, right, in order to achieve some goal that could be, let's say, an organizational goal, something like this. So that is basically your system. um let's talk about the model. So model can be defined as an artifact that can represent or mimic real world processes. So artifact is something observed in a scientific investigation or experiment that is basically not actually present but occurs as a result of some some investigation procedure, or because we want to investigate something. That's why we set it up. So, model is a numerical representation of how the real world works, right? Uh, we want to make different models or set up different models in order to describe our real world systems. Right, a model is a simplification of a system that it describes. And there is a trade off. You want your model to be as simple as possible, but then you need to make sure that it is properly capturing the parameters of your system. So that is very important. It's a trade off. Scientists or researchers, they prefer like simpler model, but then it should not be too simple. We need to make sure that it is efficiently describing our real world system and capturing all the required or essential parameters. So model, we could say that it's a abstraction and simplification of reality designed to include only the essential features that determine the behavior of a real system. And just giving you example of real system could be a banking system, like with what rate customers are entering to that particular bank, what is your service rate, what is the waiting time, stuff like this. um, Giving you example of an industrial system, so let's say what is your demand, what is your inventory level, what is your production rate, what is your machine utilization. So you kind of like deal with different essential features in in various systems. Talking about simplest model would be net income is equal to revenue minus expenses minus taxes. And most of the models of management science are mathematical models. And in addition, models may involve complex set of equations. Um, and sometimes modeling could be very daunting task. It could be very difficult task, and that's why we need help of technology. We need computers, simulation softwares to run simulations for us. So here are five basic steps of modeling, right? So first you need to understand your problem. First understand your like real world system. You need to define your objectives, that what basically do I need to estimate, right? Then you need to know what are your variables and constraints. Then what you can do, you can construct a model. Again, as I mentioned before, that you want to make sure that your model is simple, but it should be realistically representing your real world system. Third, you test the model's ability. And then fourth step would be to derive a solution from the developed model. Then in step 5 you apply the model solution to the real system and document its effectiveness. If it is doing job perfectly, then I would say no need to change your model. However, if you still need, or if you still feel the need of improvement, so it's a very good idea to jump to step 2 and add um, or remove different variables, or revise that model if required. If it is not required, and if it is solving your problem, then it's there is usually there is no need to change your model. Here is your model classification. So first one would be physical prototypes, second one could be analytical mathematical model, third one is computer model, fourth one would be descriptive model. In that particular one we are basically doing performance analysis, and prescriptive, in which we are doing the optimization of our model. So the first one was our physical model, and here you can see a car prototype, giving you example of let's say if you want to find out the braking distance. So it's a very good idea to do simulation on, or do modeling on a car prototype, right? And you would like to know that what is the uh, braking distance for a particular model of car, and how much stresses would be applied to various portions of that car in case of a crash or accident, stuff like this. And that's giving you another example of prototypes. Let's say if I want, I'm designing a turbine. So what I would do, I will make a small prototype of that particular turbine, because I would like to know that at what particular RPM I would be running that turbine, and at what should be the load on, or how much should be the load on that turbine to get maximum efficiency. What should be my head in meters, because a turbine is like quite large in real, and we cannot test a turbine in a lab. So what we do, we basically make a prototype, because a real turbine, I guess, would be requiring 1/4 river of water for testing. So that's why we, for convenience, we make like small prototypes, and we kind of develop efficiency curves for various turbines. Second one would be analytical mathematical modeling. So here we have a server, and customers are entering at a rate, let's say lambda, and mu is their service time. So I would like to know that for how much, like what was my maximum queue length, how much was the waiting time for the customer, and stuff like this. um, how much, like, in such scenarios, I would like to know, do I need another server or not. But you can just make a blind decision, because I have a queue, so I need another server. You need a proper model for that. Why I cannot just make a very quick decision without doing modeling? Because if I'm opening another server, it costs money. I will be hiring another person, I will be providing them some space and different facilities. So that is why, before opening another server, it's a good idea to model your system and know that what are your various systems parameter, and how your system is performing. In computer modeling, basically we are using Monte Carlo simulation. So in Monte Carlo simulation, we are drawing samples from the whole probabilistic region. We are not talking about deterministic events. We are sampling from whole uncertain region or probability model, and then we are running, let's say, 10,000 or 20,000 or maybe more iterations, right? And results could be displayed with the help of box plots, in order to cover the whole uncertain region. That's basically Monte Carlo simulation for you, and I think that's our lecture 3 or 4 also, uh, which is related with sampling. 3 and lecture 4 is basically my Monte Carlo simulation. Let's talk about descriptive modeling. So, giving you example of a maritime project in which they are modeling different. You're modeling various routes of vessels or ships, and the objective is to minimize the accidents, right? So this research was basically performed by Professor Van Dorp of George Washington University. On his web page, official web page, he's providing details of this maritime vessel project. So I will definitely encourage students, or recommend them, to have a look at his official page and read about his research. Here, this is a very simple example of a production control problem. So we have a raw material, and then we are basically doing some process to transform our raw material into output, right? And we are sending that produce output to warehouse, and if we can fulfill that demand, That would be nice. If we cannot fulfill a demand, we will be losing a customer. So we have a packaging, warehouse, housing process. Product is filled, sealed, and put into boxes. Boxes are taken to warehouse. Customers arrive with product time. So this is basically the interpretation or depiction of that figure. Now, regarding previous slide, we mentioned that if we cannot fulfill demand of a customer, we will lose that customer. So here are few design and performance related issues. That can we improve the customer service level, or like percentage of customer whose demand is completely satisfied, because we don't want to lose customers. Second would be, is the machinery underutilized or overutilized? So in this one we are talking about machine utilization. The third one, is the maintenance level adequate? So what whenever you are modeling your maintenance, so you are not usually, it's recommended not to take deterministic value. It's a very good idea to model um, the machine failures or machine maintenance as probabilistic, right? The last one is, what is the trade-off between inventory level and customer service level? Yeah, because you don't want to keep inventory level, or you don't want to put too much material in your warehouses, because there are hidden costs associated with inventory. And on the other hand, you don't want to lose your customers also. So you need to make such decisions in which you can balance both. It's kind of like a trade-off decision. So basically simulation is helping us to answer those questions, um, which we will study in upcoming classes or lectures. So thank you very much, and have a nice day.